So moving on. So first off, I want to talk about dispersion forces. And so importantly, dispersion forces have a bunch of different names. So sometimes they're called London dispersion forces. They can be called London forces, or they can be called van der Waals attractions. And so they all mean the same thing. These are the weak interactions that you find between all molecules. And so that's made in this point here, that all molecules, all of them, whether they're non-polar covalent compounds or polar covalent compounds or ionic compounds, have dispersion forces. And so they're found on all molecules, but they're very weak interactions. And so what I have here is a description as to why these interactions are so weak, but I'm going to explain this on the board. Can you decrease the slide? So on the board here, I want to sort of describe how dispersion forces come about between molecules. And so again, I have here an example of a covalent compound, which is methane. And methane has an extremely low melting point and boiling point. And the reason is the only kinds of forces between the methane molecules are these weak dispersion forces, so it doesn't take much energy to break these forces and to liquefy or to boil methane. And so methane will be a gas at room temperature. But let me talk about what these forces are. So here is a picture of methane, and so I try to draw a three-dimensional picture of it. Here is carbon in the center, and we have single bonds to two hydrogens here, another hydrogen heading out toward us, which is a single bond, and then we have a single bond of hydrogen going into the board here. So that's one way you can represent the molecule. But we kind of know that in these bonds are valence electrons. There's two of them. And so what we can think about is where the electrons are at any point of time. And so if you average the locations of the electrons over time, it might look something like this. And so here the molecule looks more like a blob. And so now you can see that where the electrons are kind of in the bonds toward these hydrogen atoms. And so that is a picture of what the molecule might look like. And so here is another methane molecule here. And so carb is in the center, and so the hydrogens are on the side, and they're connected here by these blobs of electron density. Now, what happens in this methane molecule, and this not only happens to methane molecules, but all molecules, but here in this methane molecule, what will happen is that you will have electrons move around over time. So now let's think a little bit more in detail about the motion of the electrons here in these molecules. An analogy of this may be, say, a hot day when you're camping, and so maybe you have some perspiration on your head, and then you have these gnats that are attracted to the perspiration. And so think of the gnats as electrons. And so the gnats are kind of buzzing around your head, but that maybe in a point of time you'll have a couple more gnats on the right side of your head than on the left side of your head. So there are times where the gnats tend to be focused in different places around your head. Same thing with these electrons, in that there will be brief moments of time where you'll have sort of a focus of electrons in the molecule. And so maybe for a brief moment, here they're in this spot here. Maybe there are a little bit more electrons here, or electron density than normal in this particular spot here. So if that's the case, because electrons have a negative charge, then what we can say that this has a relative excess of negative charge just for this moment here. And so it'll be delta negative. Now what happens is, if you have a delta negative on one molecule, it will induce a deficiency of electrons in the neighboring molecule. So here, I'm going to use maybe an open point here to show that this delta negative on this one molecule is inducing a deficiency of electrons. The electrons meaning they're kind of pushed away from this area, and this will be delta positive. And so this delta negative, delta positive is a very weak attraction, and this is the dispersion force. And so one of the things you can imagine is that this is going all over these molecules. And so there are a lot of these dispersion forces here, but they're so very weak, they really don't do a great job of holding these molecules together. So you can get methane cold enough where these dispersion forces will kind of lock the molecules in place to form a solid, but you don't need much temperature to get them to melt. methane probably melts at about negative 190 degrees Celsius. And then you can at that point have the methane molecules have a few dispersion forces kind of holding the molecules together, but then they will vaporize at some temperature, say like, I don't know, say like negative 40 degrees Celsius, and then the molecules fall apart. And so when you're at room temperature, then methane will be in the gaseous state. So very importantly, all molecules have dispersion forces because all molecules have electrons, and all these electrons in these molecules have this kind of property where they can focus at one place. So if I can increase the slide. Okay, so now what I'm going to do is I'm going to talk about another interaction that occurs between covalent molecules, which is called a dipole-dipole interaction. This is found only in polar molecules, and these attractions are a little bit stronger than the dispersion attractions. So if I can decrease the slide. Okay, so here I'm going to use this molecule called chloroethane to describe what a dipole-dipole interaction is. But before I do, let me just remind you that because these are molecules with electron clouds, that these molecules also have dispersion forces between them. But again, it's important to point out, due to the molecule structure, it has that additional interaction between the molecules, which is called a dipole-dipole interaction. So this only occurs with polar molecules, and I think you'll see why this is true in a minute. So first, let's look at the structure of one of these chloroethane molecules. So we have two carbons here, and then we have hydrogen surrounding the carbons, but then in place of one hydrogen, we have a chlorine. And so maybe one of the things you learned in class was that here, when you have a molecule that has all nonpolar bonds, it is a nonpolar molecule. So the carbon-carbon and the carbon-hydrogen bonds are considered to be nonpolar bonds. However, the carbon-chlorine bond is considered to be a polar bond. So because we have this one carbon-chlorine bond, this is actually a polar molecule. Here's another way to think of it. So again, there's really no dipole moment that we can draw between the carbons and the hydrogens here, but because the carbon-chlorine bond has carbon and chlorine in it, carbon has electronegativity of 2.5, chlorine has electronegativity of 3.0, that classifies it as a polar bond. So we can draw a dipole moment like that. So the base of the arrow begins at carbon and ends at chlorine. And so what that tells you here in this bond, that the chlorine is the relatively delta negative end of the bond, and the carbon is a relatively delta positive end. Now, you can sort of now clearly see that the rest of the molecule is pretty nonpolar, right? But on the other side of the molecule, we have some interesting things going on. We have a delta negative side and a delta positive side. And so overall, the molecule has this unbalance between the left end and the right end. If it's unbalanced between the left end and the right end, it is a polar molecule. Now, one of the things we can do is we can just take a look at the molecule on the whole. And so what I'm going to do is I'm going to just draw the molecule as an oval like this. So let me draw the oval down here. So here is the chloroethane molecule. And what we just kind of figured out, there's one end where not much is going on, right? But then there's the other end where the chlorine part is delta negative. So the chlorine part of the molecule is delta negative. And so relative to the chlorine side of the molecule, which is delta negative, here the other side can be considered delta positive. And so here this molecule has a difference of partial charge across it. So one end has a slight deficiency of partial charge on one end has a slight excess of partial charge. And so when you have a molecule that is like this, then it's said to have a fixed dipole. So this molecule has a fixed dipole, and so another way you can think of it is rather than looking at a single arrow here for a bond as a dipole moment for the bond, we can consider the whole molecule as having a dipole moment. This is called a molecular dipole moment. So this chlorine ethane molecule is going to be exactly like this one. So what we can do is we can put this molecule here, right next to the first one. So this is delta positive and this is delta negative. And so here this has a molecular dipole moment as well. And so what you can imagine is that the delta negative area from one molecule is going to be attracted to the delta positive area of another molecule. So this interaction here between these molecules, these polar molecules, is called a dipole-dipole bond. And the reason why it's called that is because you can think of these polar molecules as having a molecular dipole, and it's attracted to the next molecule over, which is also a molecular dipole. And again, not all covalent molecules have these. For example, nonpolar molecules do not have dipole-dipole bonds. We must have a polar molecule. If you have a polar molecule, then it'll probably have a dipole-dipole bond. Okay, so if I can increase the slide. So there is one more interaction I need to describe. This is a particular kind of interaction called hydrogen bonding, which can occur between some covalent molecules. And so hydrogen bonding is also only found in polar covalent molecules. It is also only found in a subset of polar covalent molecules that have dipole-dipole interactions. And so to understand what a hydrogen bond is, you have to understand what has to be on the ends of the hydrogen bond. And so one end of the hydrogen bond requires something called a donor, and the other end requires something called an acceptor. So a donor is a hydrogen atom on an electronegative atom, which could be oxygen, nitrogen, or fluorine. An acceptor is an electron pair on an electronegative atom. So for example, water has hydrogen bonds between its molecules, and I have some pictures there that describe this, but what I want to do is decrease the slide and sort of describe this on the board. Okay, so for the last molecule we're going to be looking at is the water molecule. And the reason why I want to look at that one is that is a great example of a molecule where you see hydrogen bonds between the different molecules. Now, I want to point out that water also has some of the other interactions that I mentioned earlier. So all molecules have dispersion forces, and so water is a molecule and it will also have dispersion forces. Now, water is a polar molecule, and maybe you might remember is that all polar molecules have something called dipole-dipole interactions. So what I want to do now is just digress a little bit and just sort of show you where the dipole-dipole interactions are in water molecules. And so let's go ahead and just kind of look at this water molecule here on the left, and let me show you where the dipole-dipole interactions come about between the molecule on the left and the molecule on the right. So here you might remember that when you have a bond between hydrogen and oxygen, this bond has a shared pair of electrons. And so the shared pair is probably going to be spending less time around hydrogen and more time around oxygen. And the reason is hydrogen has a lesser electronegativity of 2.1 and oxygen has a higher electronegativity of 3.5. So the way we indicate that this bond is a polar bond and that maybe the shared pair of electrons are spending a little bit more time around the oxygen is we use a dipole moment arrow, which I'm kind of drawing in red here. So we have a dipole moment arrow for this hydrogen-oxygen bond, and so we'll have one for this one as well. And then you have to remember that there will also be dipole moment arrows from the nucleus of the oxygen atom out to the lone pairs. And the reason is the nucleus of the oxygen atom is a positive charge because that's where protons are, and lone pairs are negative. And so I can sort of draw those in as well. I'll try to draw those in. So we have a dipole moment going in this direction and a dipole moment going in this direction. So one of the things you can see right now is that these bond dipole moments do not cancel out in space. In fact, if anything, they kind of reinforce each other. And maybe what you can sort of see is that we have the base of the dipole moment arrows on the hydrogen side of the water molecule and the ends of the dipole moments toward the oxygen side. So that basically says is that you have electron density kind of leaving hydrogen and going out to oxygen. And so we can represent that, if we wanted to, by writing a net arrow here. So the net arrow I have in white here. And so this is the net arrow that kind of shows that the electron density is leaving hydrogen and going out to oxygen. This is called a molecular dipole moment or a fixed dipole moment. Again, that's a little different than these bond dipole moments. This is, again, the net of these bond dipole moments to give you this molecular or fixed dipole. Okay, so now what you can sort of see now is that the hydrogen ends of the molecule are going to be kind of deficient in electron density, so it's delta positive. And same thing with the oxygen. It's going to be in excess of electrons, so it's delta negative. And so the same stuff will be going on here. So here, the hydrogen ends are delta positive, and then the oxygen end is delta negative. And so this will also have a fixed dipole moment. So the question is, where is the dipole-dipole bond between these water molecules? Well, again, we can sort of think of this water molecule as just maybe as an oval with a delta positive end and a delta negative end. Same thing with this water molecule here. And so you can see that the delta negative end of one water molecule, which is near the oxygen, is going to be attracted to the delta positive end of another water molecule, which is the hydrogens. And so here, this attraction is called a dipole-dipole bond. And again, this occurs because water is a polar molecule. Now, in a subset of polar molecules, you can have an additional stronger attraction called a hydrogen bond. So I need to talk to you about that. So water not only has dispersion forces and dipole-dipole interactions between the water molecules, but there are hydrogen bonds between the water molecules. So the way we know that there are going to be hydrogen bonds between the water molecules is that if you look at the water molecules, you'll see that there is a hydrogen bond donor, which is a hydrogen atom on an electronegative atom, on one molecule, and a hydrogen bond acceptor, which is a lone pair on an electronegative atom, on another molecule. So let me show you where those are. So let's just focus in on this right water here. So here, you see this hydrogen here? It's hydrogen stuck onto a ferroelectronegative atom, which is oxygen. So we can think of this as the hydrogen bond donor. And so for the reasons we were kind of talking about before, we would expect that this hydrogen bond donor, because its shared electrons are being pulled away from it toward the oxygen, will be relatively delta positive. Now, on the molecule on the left, that is where we find the hydrogen bond acceptor. And so that would be the lone pairs on the oxygen atom. So let me mark this as acceptor. And so one of the things you might remember is that the oxygen is delta negative. So we have one water molecule with a delta negative end, which is the lone pairs on the oxygen atom. And we have another water molecule with a delta positive end, which is the hydrogen that's kind of bound to this electronegative atom. And so you get a bond formed. Now this bond here is a little bit stronger than a dipole-dipole interaction. And so that is one of the reasons why that water, compared to a lot of different liquids out there, has a relatively high melting point and boiling point. And we'll talk a little bit more about that later. So thank you for listening. We'll see you next time.